Hello everyone, my name is Salman and very recently I started this online educational platform. Today we are going to discuss the topic of physics and the topic is equation of a wave. So let's try to find out what is an equation of a wave. For trying to understand what is equation of a wave and how do we derive it, let's first of all understand what is a wave. So a wave is defined as a disturbance in a medium that carries energy without net movement of particles in the direction of wave, right? The particles do not move in the direction of wave, they only oscillate, which we are going to see very shortly. They oscillate in their positions. Let me, give you an example to explain this, to elaborate this, and then we'll go to the topic. For example, this is a basketball post, and a person is standing here with a basketball. Suppose he has to carry this ball and put it in this goal post. What he'll do? He'll just walk here, run whatever he can, and then go and put the ball where it is required to be put. Now, for example, if there are many persons standing just side by side, and instead of one person carrying the ball and putting in the post, one person gives to another person, he gives to next, and so on till the last person goes and puts it in the post. So now you can see till this person, nobody has moved from his position, but the ball has moved from this place to this place. Just to explain you that wave doesn't carry the particles of the medium along it. Wave only transmits the disturbance from one position to another, and particles only oscillate in their positions, and we'll see how. Let's take a few examples of wave. First of all, as we have already said, the particles of the medium are set in oscillation, and that's how the disturbance is carried. Now, depending upon the direction of oscillation of particles, please note it, waves are classified in two types. One is transverse waves, where the particles oscillate perpendicular to the direction of propagation. Suppose the wave is propagating in this direction, the particles are oscillating in their position in such a way that their oscillation is perpendicular to the direction of propagation. You can see here, these are the movement of particles just shown by some arrows. The other type is longitudinal waves. In these kinds of waves, the particles oscillate along the direction of propagation. Means they don't move along with the wave, they only oscillate in their position. The only thing is that this direction is along the direction of propagation. That's it. For example, this is the direction of wave propagation. So every particle moves like this, he comes back, again he moves like this, again he comes back. So you can see transverse wave, the shape is crest and troughs. These are crest, the top points, and these are troughs, right? T, T, and T. Okay. However, the longitudinal waves moves in the form of compressions and rarefactions. See, these are compression, see, where you can see, the matter is compressed, and these are rarefactions. Till you can see here, these are all rarefactions. Hope it's clear. Again, let's see some animations. It will be more clear. Now, animations which are depicting transverse and longitudinal waves. This is an animation which depicts transverse wave, this one, and the other one depicts a longitudinal wave. It is clear that the medium particles are only oscillating in their position, but the wave is moving in this direction. You can see. Now I've just put a straight line here on this particle, which is marked in red. So you can see it is going up, it's coming down, again it goes up, again it comes down. So its position is this, it's only oscillating about its position. Similarly, in case of longitudinal wave, you can see this is the mean position, and the red one, that matter is oscillating about its mean position. Just see this red mark. It goes here, again it comes back and goes on the either side, and again it comes back. I hope it's clear. Day-to-day example of transverse wave, which are transverse wave on water surface. When you put a stone in a pond, you throw a stone in a pond, these kinds of ripples are created. You can see their transverse waves are generated. Now, if you just put a cork here, you will see that cork only oscillates up and down. It doesn't move in the direction of disturbance. The direction of disturbance is, this is the direction of disturbance because these ripples are carried to the shore, right? But anywhere you put a cork or anything which floats, you will see that it only oscillates up and down, right? I think now you will have a fair idea what are waves. Now, the wave equation is written in this form. You must have seen in books. Y is equal to A sine omega t plus or minus kx. Y is a function of x and t. What does that mean? It means y is position of a particle at a distance of x at time t. And this is how we write. Instead of y, we write y, x, and t. In some books, they don't write xt. It's okay. But many places, it is written like this. So don't get confused if they don't write. Already in this equation, you will have t and x. So it is just a way of writing. They can even write it y is equal to a sine omega t plus minus kx. That's also okay, right? But if in some books they write x and t, this is also okay. Now let's understand how the equation of wave is derived. It's very important and quite interesting. Step by step, I'll show you how the equation of wave is derived. Please listen very carefully. Now we can take either of the longitudinal or transverse wave, but let's take transverse wave. The same is the case of longitudinal waves. Now you can see this is the shape of the wave. What I just showed you uh, in ripples, in the form of ripples in the pond. So if you take a cross section of the water surface, any place, suppose these are the ripples which are being formed like that. So if you take any cross section like this and cut this, so the shape is going to be like what I have depicted here, this one. Now this is the mean position of the liquid. Before the wave came, this was the position, and when the wave moves from this in this direction, the particles only oscillate about their position, and it looks like this shape is being carried forward, but it doesn't get, material doesn't move, only they oscillate, and this kind of shape is generated. So now particles only oscillate. For example, this particle goes to a maximum position and again goes to maximum position in this direction. That means every particle either will go A in positive direction if A is the amplitude of the wave, or A in negative direction. Now the question is how to represent this wave. What mathematical expression will you use in representing this shape? Do you have any idea? Just pause this video and think about it. Which curve can be used here? I think some of you may be having some idea that let's recall our or revisit our trigonometric functions, curves of some trigonometric functions. Now, this is one curve. I hope you must have read it. +1, -1, which is the curve sin x. Similarly, you will have purple one is cos x. You have seen that either it is sin x or cos x, they both lie between +1 and -1, and their shape is also similar to the wave. The amplitude is either +a or -a of any particle. Here it is +1 and -1. I think if we try a bit, we can represent a wave through these curves, taking the help of these curves. So we can take either of them. So we can use either of them to represent a wave. Now, anyway, before proceeding further, let me give you one or two important concepts which will be used further. Let me explain you that. For example, if you are using this curve of y is equal to sin x to represent a wave. Now this 0, pi by 2, pi, 3 pi by 2, 2 pi, they are called phase. Phase, what do we mean by that? Now 0 means the particle is at its mean position. Pi by 2, it's at its maximum position in one direction. Pi, again it comes to mean position. 3 pi by 2, it is in maximum in other direction. 2 pi, again in mean position. And any at any place, say for example, if you have any phase like phi, that means the particle here is here and it is moving upwards. Suppose there is a particle here which has phase of phi dash, that means the particle is here and it is moving in the downward direction. That means, what does phase represent? Phase of a vibrating particle expresses the position, this phi, this is the position, and the direction, whether it is in this direction, this is phi dash, which, or this direction of motion at any instant. Now, if lambda is the wavelength, what is a wavelength? You must be knowing that this is the wavelength. It's the distance after which the pattern repeats. You can see here, this is the mean position, and again after the distance of lambda, again the same pattern is repeated. So this is called a wavelength. Now we can easily see that this is the path which the wave has traveled, lambda. This path means a phase. Suppose the wave is traveling in this direction. So consider this particle and this particle. So there is a phase difference of 2 pi between them, from this particle to this particle. 2 pi of phase difference is equal to path difference of lambda. That means unit path will have a phase difference of 2 pi upon lambda. X distance will have a phase difference of 2 pi upon lambda into x, right? Path difference of x will lead to a phase difference of 2 pi upon lambda into x. Hence we write phase difference is equal to 2 pi upon lambda into path difference. If you have a path difference of x, which means there is going to be a phase difference of phi, where phi is equal to 2 pi upon lambda into x. Let me again explain you, give you more clarity. Suppose this is the wave. If the path difference x produces a phase of difference of phi, then phi is equal to 2 pi upon lambda into x. I hope it's clear. One more important concept. Suppose there is a particle at a distance x1 having a phase phi1, and there is a particle at a distance x2 having a phase phi2, and if the wave is traveling from left to right, then the particle at position x2, this one, which is right now in this position will lag in phase with respect to particle at position x1, that is, which is at this position, because the wave, since the wave is moving in this direction, so first it is going to touch this particle, which is at x1 position, and then it is going to touch this particle which is at x2 position. So definitely particle at x2 will lag in phase. This is an important concept. Please remember this because we will be using it. But if the wave is moving in reverse direction, means from right to left, then particle at position x2, this will lead in phase with respect to particle at position x1, because wave is going to first touch this particle and then it will come to this one at position x1, right? Now this is the shape of the wave which we have already discussed. So whatever we have learned till now, for example, at a distance x, if there is a phase difference of phi, so for this particle y, can we write like this: y is equal to sine phi. There is one thing which is missing, which is a sine phi, or y is equal to a sine. Now phi is equal to 2 pi upon lambda into x. It can be written. That means this will become the equation of wave. So can we write equation of the wave for any particle at a distance x as this? It's a question to you all. Just think over it. And very shortly, we'll be getting the answer. So let's test it. Let's check by giving different values to x. 0, lambda by 4. This is x is 0. At this place, it is lambda by 4, lambda by 2, 3, lambda by 4, and till here it is lambda. So we get the values as of y at 0, lambda by 4, lambda by 2, 3, lambda by 4, lambda as 0, a, 0, minus a, 0. Let's check it. X is equal to 0, y is equal to a sine 0 is equal to 0. That means we get this point in red. X is equal to lambda by 4, y. X is equal to lambda by 4, y. Now this is your lambda by 4 is equal to a sine 2 pi upon lambda into lambda by 4. That means pi by 2. And sine pi by 2 is 1. It will be a. That means the next point we got it. This one. It's correct. Now, for lambda by 2, this is your lambda by 2. X is equal to lambda by 2. Y is equal to a sine 2 pi upon lambda into lambda by 2. A sine pi, which is 0. That means this one, red color. So you can plot other points. This 3 lambda by 4 and lambda, you will get these points. Positions which are plotted in red are in perfect agreement with our wave. That means equation of the wave should be this. This should be the equation of wave. That means we have got the equation of wave. But there is a small deviation here. We have missed something, and I'll tell you why. The wave is moving with a velocity v, like this. So after some time, what will happen? Its shape changes with time. Now, where are your positions? This particle is now in this position. This particle is moved to this position. This particle has moved to this position. This particle has moved to this position, and this one is now in this position. That means whatever the equation we got till now, it represents only positions at a particular time. That means at some time this is the position, but at the other time the position is different. That means we have to incorporate time. So if we take snaps of waves at different times, it will appear that whole material is moving if you take the snaps, but we know that material does not move, particle only oscillate, but it gives a feel that whole material is moving. For example, if you take the snapshots of wave at different times, say wave at time t1, this is one snapshot cross section. At t2, this one. At t3, this one. Now you just see, it appears that this material all is moving in this direction, right? It is moving in this direction, but it's not. Just see this particle. At t1 it is in this position. After some time it moves to this position. Again it moves higher. Consider any other particle. This one, it is in this position. Then it comes to mean position. After some time it moves again in this position. So you can see the particles are only oscillating about their position, but times it gives a feel that the whole material is moving. It's not. Let me explain you further. Another example will make it even more clear. For example, this is the direction of wave propagation, and these are the particles on the surface, which I have marked in blue, red, and yellow, and all those colors. Wave has only reached till this place, and wave is moving in this direction. So this is the surface of the liquid, this one, whatever it is. Here the surface is plain because wave is yet to reach this place. Slowly the waves move forward. Now just see. Take any particle, take this blue one. It is in mean position. Then it moves in this direction to this position. Again, it moves further. Then it comes back and it comes to its mean position. Take the case of red. It is in this position. After some time, it moves like this. It again comes to its mean position and it is in this direction. And after some time, it is in this position. So you can clearly see that particles are only oscillating about their mean position. A very good, depiction in this animation. I put a purple line. Just see this particle, this one, which is moving along the purple line. This one, right? I think it's very clear to you. Now, what we have learned so far, we have learned that movement of the wave is due to oscillation of every particle in its position. Hence, if we find the equation which shows position of any particle and, please note it, and its variation with time, this will represent, or this will become the equation of wave. That's all. Now consider a plane progressive harmonic wave moving in positive x direction as shown above. If we count the time from the instant the particle at O passes through its mean position, we count the time as at this time when it passes through its mean position, t is equal to 0, right? Then the displacement of O can be written as y is equal to a sine omega t, because O will only oscillate about this position. It will go up, then it will come down. So it will, if amplitude is a, it will go a here and then come minus a in this direction. So this is perfect. O can be, the particle at O can be represented by this equation. But for equation of wave, you require to have the position of any particle with respect to time, right? But we'll take the help of this. Now, consider a particle at position P, which is at a distance O from its mean position and has a phase lag of phi with respect to O. Now, position of P, displacement y can be written as a sine omega t. This is for only O, but this particle at P will lag in phase because wave is moving in this direction, minus phi, right? That means displacement of particle P at any time can be given by a sine omega t minus phi. But we know that phi is equal to 2 pi upon lambda into x. So the equation of wave now becomes y is equal to a sine omega t minus 2 pi upon lambda into x if the wave is moving in this direction. But if the wave is moving in opposite direction, at that time P will lead O. So its displacement can be given by a sine omega t plus phi. And phi we know is 2 pi upon lambda into x. So if the wave is moving in this direction, the equation will be this one. Hence, we can write the equation of wave as omega t plus minus 2 pi upon lambda into x. But v is equal to n lambda. That means lambda is equal to v upon n. V is the velocity and n, v is the velocity of wave, and this is the frequency. So 2 pi upon lambda becomes 2 pi upon v upon n is equal to 2 pi n upon v. Now 2 pi n is equal to omega upon v. This is called angular wave number, and it is denoted by k, right? So then the equation assumes this form: y is equal to a sine omega t plus minus kx, which is the equation of wave. I hope you understood this derivation. It's clear to you how we derive the equation of wave. That's all in this topic, and hope you enjoyed it. Thanks for watching this. Have a nice day.